Scott.
Jeremy Scott Hoffman. Jeremy.
All right, thanks so much, Rich. That's exactly right. So, like, the biggest thing is that there is a lot of misinformation out there right now, and probably going to be a lot more for a number of reasons. So we're just going to go through what we know, how we know it, and what we can do about it. Okay? And at any point, if something is confusing, if something doesn't smell right, just raise your hand and ask me a question. I'm here all the time. I'm a resource for all of you, a resource for, anything Earth climate related, okay? So this is something that I really value as a skill set of mine, and I'm happy to spend time talking about any of these individual details that you might want to know more about. So anyway, the title is just what the heck is going on with our climate anyway. This hopefully isn't a new thing for any of the people in this room, is that global temperatures are increasing, and they are steadily breaking new records every year. And when we look at something like this, so this is a graph that was published in the Intergovernmental Panel on Climate Change report in 2013. This is the most recent synthesis of all the available global data that we have relative to climate change, okay? So this is 1850 back here, and this is the early 2000s, 2000 to 2010. Because we are currently living in the 2010s, we don't have that decadal data yet. But this trend has continued, no surprise there. But when we look at from 1850 to the early 2000s, and on the y-axis we're looking at temperature, global temperature relative to a baseline, is that there seems to have been, kind of interannual, maybe some sort of other sorts of things like El Nino, La Nina cycles and stuff. But overall, over at least the last 100 years or so, there's been a pretty steady warming of the planet. Yes?
What's the source of like 1850s data?
Right, so that's a really good question. So it actually takes a lot of effort on the part of scientists to amalgamate all of what we do have. So there are individual records from boats, ships that go out, and they've taken sea surface temperature data. It's really sparse. So the thing is that we have to use statistical relationships to move that temperature patterns that we see regionally to make a global picture. Now, really, the best data that we do have starts in about the 1950s to 1970s. So, but this is still something that, all of these different lines, these different colors, are individual data sets that have been used to show the exact same thing. So we're really confident that we know, based on real modern thermometers, that this is a stable thing. So when we look at just the individual decades on the same kind of temperature scale, every decade for the last 30 years has been the warmest one of our modern thermometer record, and this one is certainly on pace to be the warmest also, because 2016 is already going to be the warmest year ever. 2015 is currently the warmest year ever, and third place is 2014. So it seems like this is happening. And we don't just have modern thermometers. Scientists have actually figured out natural thermometers. So there are things in the world that are sensitive to temperature. So this includes ice cores, bubbles that accumulate in the vertically accumulating snow in the polar regions. There are also tree rings that are sensitive to temperature. And things that accumulate in caves are also sensitive to temperature. When we start to amalgamate all of the information that we have from those things, we can go beyond our modern thermometer timescale and start looking at timescales more on the order of, multi-century types of patterns. And this is a paper that was published actually the day I defended my PhD. In Nature, and what this does is it separates global temperature anomalies from these natural Earth thermometers into land and ocean temperatures, and this just gives further evidence that what we're seeing over the last 100 years or so is really starting to identify that the Earth is being pushed in a certain direction, and that it's warming. Okay, but we don't just have temperatures. Good thing about global temperatures, it also affects other parts of the world. And we have plenty of data to suggest that this warming is having an effect on other parts of the world, other parts of the climate system. So we have 4 panels here. On each one, they're all running from 1900 to into the 2000s, from left to right. And on these different y-axes this is snow cover in the northern hemisphere in millions of kilometers, square kilometers. We have Arctic sea ice, which is a big deal right now, and we'll get into that. And then we have global average sea level change and the heat accumulating in the ocean. And if we look kind of just at sea level changes for a number of reasons. So the biggest one being that as ice that's on land turns into water, it's basically like moving money in 2 bank accounts. So we've got a bank account on land, that's ice. And we've got a bank account, that's the ocean, that's in water. And when we move one from the other gets larger. So when we melt ice, we move that from one account to another, and then that grows our ocean account, basically. So we're adding water directly to the ocean from ice melting on land. Also, as the ocean has been warming up, it expands. So it actually fills a greater volume. This is called thermal expansion. And in the way that we can think about this is anytime that you make tea, anytime you make pasta at your house, you put a pot of water on the boiler, and as it warms up, it starts to bubble, it takes up, and it might actually boil over. It's the same principle. It's basically the water is expanding to taking in that thermal, the thermal energy and expanding. Another way that it can change, at least locally, is that as the Earth actually kind of moves up and down, it can make sea level rise faster in certain places than others. And that's actually something that we're seeing here in Virginia. So this is Sewell's Point, the best tide gauge really that we have in this region, and sea levels have been rising about 1.5 feet, or the rate that we're seeing is about 1.5 feet per 100 years. And this integrates, the thing about Sewell's Point in Chesapeake Bay is that it integrates all of those reasons that sea level can change. So globally, sea level is rising because of land ice melting, and the ocean expanding because it's absorbing heat. But in Virginia also, we're sucking water out of the ground at this obscene rate, such that the land underneath is being compacted. So it's actually the coastline here is sinking, also due to our need for water. Anyway, so that's making local sea levels rise much faster here than they are globally. But when we start looking, so those human activities can actually be parsed out of natural versus kind of human-caused sea level rise. This is probably a really good way to look at it, is the number of flood days at Sewell's. This is using Sewell's Point data, and you can see the number of flood days has been increasing over the last few decades, and the number of those that can be attributed to human activities is also increased. But it's not just Sewell's Point. We can look globally at sea level rise rates over the last couple thousand years, and it seems like the sea level rise rate that we're seeing right now is the fastest it's ever been, at least as far as we can tell, back to the 1st century. So that's 2,000 years. So we're definitely seeing sea level rise at a rate that is not natural. It's been fluctuating between about +3, -3 inches over the last 2,000 years, and then here's the 20th century, and there's a lot of evidence to support that this is actually accelerating. It's not just sea level, so let's look at some other point of the world. It should be getting a lot more attention right now, but it's not. It's Arctic summer sea ice extent. So this is in the summer, so the lowest point of the year is the beginning of September. Okay, and every year since we've started looking at it really in the satellite record since the early 80s, late 70s, has been slowly getting lower and lower. 2016 had the lowest summer sea ice extent, just behind 2012. And if we start looking at ship records and observations from earlier part of the century, this has been going on for almost 100 years. But we're going to look at, this is a confusing graph, but just bear with me for a second. So these are months of the year, and then we have the sea ice area in millions of square kilometers, okay? And then this is global, so you might see that there's a low point here and then 2 kind of humps. And that's mostly because, well, During June, July, and August in the northern hemisphere, when it's summer here, it's winter in the southern hemisphere. So sea ice is expanding around Antarctica. But then during the summer here, it's retreating. So we're looking at kind of the total global balance of sea ice that is seasonally offset from each other, okay? When it's winter here, it's summer in the southern hemisphere. When it's summer in the southern hemisphere, it's winter here. So there's two high points in the global sea ice area. And each one of these lines is a different year that we have data from, okay? So all the years that we have data from satellites that are orbiting the planet looking down at these regions. And red line here is this year. 2016 has been very abnormal. And we look at kind of the progression of these years. These thick blue lines are the recent 2010s. And really, this year has been extremely unique. And the way that we look at the global sea ice and the polar regions is that's the world's air conditioner. And it's currently on the fritz. It seems to be really, really something strange going on. And this was from November 12th. So I looked at this again when I was going through my slides on Saturday, and it's getting worse. This is from Saturday. So this is something, and this is something that's not being reported on in the news. This is what is usually covered, at least in some part or another, by mid-November. This part, this much of the North America, and this is how much was covered on November 14th. So this year seems to be, it's not only the Arctic that's feeling this year, this really exceptional year, it's also, most of North America. You'd have to go into really high elevations to see snow in mid-November, which is really not like the average. Here in Richmond, so let's talk about what you can say to your family at Thanksgiving. These are Richmond data. So I haven't verified the statistical significance of these relationships. I'm working with Climate Central, this group, to do just that. But at least from 1970 to 2015, we've been losing the number of days with frost. We have a longer frost-free season. It means that that's throwing off our growing season and has some big impacts on local agriculture. Also on the blooming of local flowers, maybe your own garden. These are things that we can actually start to see having an effect on local plants and how you might be planting your garden. Another thing, the summers are getting more humid. This probably, it looks to me like a much better relationship than the previous one, but since 1980, the humidity of a summer has gone up. So I don't like that personally. I'm a very sweaty person, but summers are getting steamier. That's uncomfortable for everybody. That also then coincides with our summer nights are getting warmer. And you might wonder, why does that matter? Why would a summer night be important? Well, elderly populations that might not have access to air conditioning. It's really hard for your body to regulate its own its body temperature while you're asleep, and that actually seems to be the biggest reason why people suffer mortality during heat waves. It's actually at night when they're asleep. So we are basically, this is not good for communities that might not have access to ways to cool themselves down, especially at night. So that's like a reason to start thinking about how we can solve this problem locally. And that's something that I'm going to be hopefully working with in the near future, is figuring out how the museum might work to be a agent for good in this regard. Who likes mosquitoes? Does anybody like mosquitoes? Like really, I can't wait to get bit by mosquitoes. Well, yeah, wait, who said yes? It was like, oh, bats? Yeah, bats love mosquitoes. But using a simple relationship between temperature and humidity, you can predict survivability of mosquitoes. And Richmond, we have about a month longer of mosquito season since the 80s. That's like, and it doesn't help that people, the World Health Organization has identified mosquitoes as the key pathogen vector for Zika, which is really, really scary for expecting and want to have someday children people. So I'm not good at talking about babies, all right? So, but basically, I worry a lot about this mosquito thing because not only it's mosquitoes, but there's other disease vectors like ticks that are moving farther and further north. You can like see this red movement from the south to the northeast of these like ticks and cases of Lyme disease. I was able to find the pollen lady at the Richmond Allergy Partners. Her name is Becky Colley, and she's been taking pollen counts every day since 1988. And she's been writing them down in a little notebook and then storing those notebooks away, not digitizing them, not using them for anything really, but I've discovered that she's been keeping track of this. So now I have a research intern, Jenny Scanlon, who's doing a great job for us digitizing these data. And here's some stuff that the first thing that we found by querying these data is that so the individual light blue dots are the date of the peak tree pollen in Richmond over time since 1985. Or since 1988 when the record began. And then this is just a linear regression that I've done to it, just to pull out the kind of long-term trend. And it looks as though the day of the peak tree pollen has actually been arriving earlier by about 10 days. And I've checked this versus other regional reconstructions on phenology, meaning the blooming of these flowers, these things that have a seasonal start. And this is consistent with what we see across the Northeast. So this 10-day earlier blooming period is seen in a bunch of different things. So I'm actually really excited. We're going to be working a lot on other types of pollen. She has, it's just this amazing data set that we're going to be able to spend a lot of time on and hopefully publish some really cool stuff about it. But anyway, if anybody here suffers from allergies, this is definitely not good news. But so anyway, this is just, I'm sorry for spending so much time on here's all the things that are going wrong, but this is what it looks like in a map. You can definitely see, there are still places around the earth that we don't have a lot of good data, but we are able to now see this from space. We're able to measure it from the ground. There's like no disagreement anymore about the data. So I'm really just hope that this is something that you all are on board with. Like, we know this is happening. Climate is changing. It led the Intergovernmental Panel of Climate Change to say that the warming of the climate system is unequivocal, meaning there's no way to say that it's not. And since the 1950s, a lot of that is unprecedented given our knowledge of the last few decades to the thousands of years, okay? Everything that I've just shown you is consistent with this statement, and there's no longer denying that the climate is changing. Now, what people still like to talk about is what exactly is driving this change. That's the one thing that's still, like, everybody's still fighting over, not climate scientists. You hear, it's just a cycle, or the closely related climate is always changing. Or first it was global cooling. For some reason, people think that there were actually people publishing about global cooling, which they weren't. Now it's global warming. This is a misdirection. This is a tactic that's always used to just dismiss the whole thing entirely. And then my personal favorite is that it's a Chinese hoax. And my favorite emoji, this is my 2017 emoji, just wondering what is happening. Anyway, so we're gonna talk, I will help us go through what we know about what causes climate changes and what kind of timescales they operate on, so that you can say, like, if someone says, hey, this is all volcanoes, no, it's not. Turns out, so we're gonna go through the things that cause natural climate change, okay? First and foremost is that the Earth's orbit around the sun changes. We are on an elliptical orbit, meaning that we are egg-shaped, not circular, and that egg-shapedness gets more extreme on timescales of about 100,000 years. Okay, hundreds of thousands of years. That's one way that the orbit changes. Another way is that the tilt of the planet that gives us our seasons gets more or less extreme. You can think about it, if I had a bald spot and Rich was the sun, and as I dip my head closer to him, yeah, I get a worse sunburn on my head. when the tilt gets more extreme, our seasons get more extreme, okay? But that changes at 41,000 year timescales. 41,000 years. The last thing is where our planet is positioned at the farthest and closest that we are from the sun during our orbit. So that's like another thing. It's called the precession of the equinoxes. That changes on 22,000 year timescales. So all of the things that change about the Earth's orbit change on tens of thousands of year timescales. And that's what gives us this cycle of ice ages, okay? So if you hear somebody say it's all just a cycle, they might be thinking that they're talking about this, but there is no way that anyone in our entire family tree since the start of human civilization has seen climate change because of the orbit, okay? That's just not possible. And in fact, the changes in Earth's orbit are favoring ice growth. We should be going into the next ice age right now. Would be taking thousands and thousands of years because that's how fast this operates, but we should be slowly descending into the next ice age. Another thing that we know that should have an impact or potentially have an impact on climate is the sun's brightness or its intensity, its temperature. But this, again, takes decades to centuries. This is also something that for a long time we argued about in the climate community. But our knowledge has advanced. Science has done its job, and we've decided and discovered that this is no longer a viable thing to explain short-term climate changes that we are seeing today. Then volcanoes. This is something that when people say volcanoes overpower humans in climate, it's just incorrect. We emit about 135 times more carbon dioxide per year than all of the volcanoes around the world combined. This, in order for volcanoes to match us in our carbon dioxide emissions, our heat-trapping gas emissions, Mount St. Helens would have to erupt every 2.5 hours for an entire year. Straight. That's how much, that's just. And volcanoes, because of how far up into the atmosphere they shoot dust and ash, they actually have a nearly instantaneous effect on climate. It actually cools global climate when a big eruption happens. So these are things that we have been studying for a very long time. We know a lot about these things, and we can use supercomputers to simulate their effect on global climate. And NASA and other people have done this, and thank you, NASA, because now we can look at this. So here is time, again, from left to right, 1880 to 2016. These are the observations of global temperature over that time period, okay? This is what we see from, these are 5-year averages, and there's warming. There it is. Now we can say, supercomputer, show me what the global climate would have done if we just had volcanoes. Whoops. Doesn't explain global climate change over the last 100 or so years. Then we can say, computer, show me what happens when we look at just variations in the sun's intensity. Whoops. Doesn't have any effect on global temperatures over the last 100 or so years. Computer, tell me what about the changes in the Earth's orbit? Whoops. Doesn't do a lot to global climate change. So, if we add all these things together, computer, please tell me it's something natural. No, we can't quite capture global climate change using these things that we know are happening in the natural world. So that leads us to ask, okay, all right, so those natural things that everybody talks about can't help us. What else changes climate? Well, we do. Humans do. Humans have a huge effect on this. Land use change, deforestation. If you remove vegetation, that has an effect on its reflectivity to space of solar energy. And if we have coal, coal is something that is very popular. It's not really, but anyway, aerosols from coal burning, sulfate aerosols, they actually serve to cool the planet. Ozone pollution. Ozone is created through a number of processes, but low-lying ozone actually has a warming effect. And then the biggest one that we know about recently, and since 1824, is the adding of heat-trapping gases to the atmosphere. The greenhouse effect, we've known about that since 1824. 1824. It's not something that came out in the 70s. This is something that has rigorously been understood for a long time. So human activities cause unnatural climate changes. if we start asking supercomputer, tell me what the combination of ozone, deforestation, and coal aerosols did to the global climate. You can see here aerosols cooling the climate. As we've burned more and more coal globally, that has actually served to cool the planet. Deforestation has a light cooling effect because it's actually causing the places that were lush and green to be kind of desertification, reflects more solar energy. Ozone has actually had a slight warming effect. But if we combine all of those things, wait, do I do that or do I go to the, heat-trapping gases. The only thing that actually causes a warming in the supercomputers, these things that actually help us predict where planets exist and where our orbits of things that we send to Mars go, heat-trapping gases are the only things that can give us the sorts of global temperature changes that we're looking for. But you can see it actually overestimates the amount of warming that we've actually seen. Now that's interesting because it means that when you combine all of the human-caused climate changes with the natural-caused climate changes, you arrive at an answer that looks quite all right. So the thing is that the global climate is changing for a number of reasons. But the only thing that gives us the answer that fits our observations is when we have the introduction of heat-trapping gases from human activities. So, climate is changing, and we know why. We know a lot about the climate system, and we know now using this, it's been known for a while, but we know why. Our best scientific understanding identifies that the heat-trapping gases from human activities are the main driver of the current warming, okay? And we're going to switch into what can we do, because that's really more important, right? The number one thing that we need to do is to end our dependence on things that create heat-trapping gases. For context, this is how much CO2 is in the atmosphere today, and this is how much CO2 has been in the atmosphere for the last 800,000 years. You might ask yourself, how would we know that? Well, as snow accumulates in Antarctica, it traps atmosphere inside of it and basically makes a series of pancakes that are full of air bubbles that have trapped the ancient atmosphere inside them. We can poke a hole or melt that ice and get the CO2 out of it and measure how much was in the atmosphere. This is basically like the heartbeat of the planet. When it's been low in times in Earth's history, that's when an ice age has happened. And then this is times when it's been relatively higher is when there's been what's called an interglacial climate. Basically, we can see that this has been going on pretty regularly for 800,000 years, and then here's where humans arrive. So we need to stop that. We need to. That's the biggest thing. But it's hard to say how we go about that. But basically, we need to end our dependence on energy sources that generate heat-trapping gases. More locally, we need to focus on educating people about things that we can do here in Richmond, here in Virginia. So there's this great program that happened over the summer that I'm really looking forward to being a part of this summer called Preparathon, where we have an understanding of the things that we can be doing right now to be ready for the things that could and probably will happen in the future, including extreme weather and then things to actually personally change your energy consumption habits. And anyway, we're going to expand on this in the next couple of years. I'm really looking forward to seeing where this kind of programming goes. We also need to promote and utilize these sorts of sustainable energies that we've been able to identify. The technology is here today. Last year, 2015, 500,000 solar panels were being installed around the world every single day. Every single day. Every day. It's happening now. And so we can all be a part of that. And there's a Richmond Solar, or Richmond RVA Solar is a group that's here in town. If you're interested in knowing more, I'd suggest getting into contact with them. Basically, we need to make the issue relevant. We need to all band together and say, this is relevant to me, this is relevant to you, and there are ways that we can solve it. So we have a bunch of really cool graphics that we've come up with in my short time here. I've only been here for about 2.5 months, but this is something that we've been able to recycle basically every month now. The take-home point is we've collectively, human civilization did this thing. We have the information to prepare for the impacts, and most importantly, I think that we have the power to fix it. So that's really that's the message here, is that yes, it's human caused. We know what's going to happen. We can prepare for those impacts, and we can fix it. We can fix it. The answers are there. We just need to start making sure that everybody's on board, okay? Yeah, all right. Thank you.